Hello, in this session, we will review limits, the fundamental concept of calculus. I list all of the sections from the chapter 2, the limits, and we will try to cover all of them. Let's start. We have a function, the graph of the function. Let's label x and y, and we have to figure out how function behaves near these points. And I did list the points, -4, -3, -2, and so on. Okay, we can see the graph is quite fancy. The graph is quite nice, but let's figure out. Limit as x is approaching -4 of f of x. At -4, function is continuous. We can see no gaps, no jumps, no asymptote. Then if we have continuity, the limit is the same like the value. Value is 2. -3. X is approaching -3. We do have discontinuity, removable discontinuity, because just one point is removed, no value. Function doesn't have a value. However, we're looking not exactly at -3, we're looking what is happening near 3. And as x is getting closer and closer to -3 from the left and the right-hand side, the graph is approaching that open dot. And that open dot is at the level -2, the height -2. Okay. Now x is approaching -2. Similar situation, just one point is removed. When x is approaching -2 from the left and -2 from the right, graph is approaching, the function is approaching that dot, and that dot is at the height -4, the value -4. In this situation, at -2, we do have solid dot, and that's the value. It means value exists, but it's different than the limit. Limit exists. It's also removable discontinuity. 0. At 0, we have no problem. Function is continuous. We just need value is the same like the limit. Then, limit is the same like the value because we're looking for the limit. This is 0. And I would say -3.6, possibly. The same for the value. A little bit more than a half. Between -3 and 4. Okay, 1. What is happening at 1? As x is approaching 1, function is like going higher and higher. It's actually doing the same thing on the left and on the right-hand side. It means the values are getting larger and larger. One thing that we have to say, this limit does not exist as a one finite number. But we know that it's going to the infinity, and we will say infinity, but this is still non-existence limit. If we will answer D and E does not exist, it's still the correct answer. But this is more justification. Okay, 2. At 2, weird situation. As x is approaching 2 from the left-hand side, function, yes, this is the left-hand side, function is approaching that dot. That means on the left-hand side, we do have -1. When x is approaching 2 from the right-hand side, function, because that's the corresponding values, is approaching that dot at the level 1. Oh, 1, positive and -1. Then one-sided limit, that's what I was thinking, to put the symbol for the right-hand side. Okay, +1, -1. One-sided limits are different. Then the limit at 2 does not exist. And we do have a reason here, justification. Value actually at 2, the solid dot is on the x-axis 0. Okay. Now, as limit as x approaches 3, no problem. Function is continuous. I think with the same limit as the value, 1.5. Okay, 4. 4, something is going on. Different situation on the left, different situation on the right, and different situation at 4. Value at 4, the solid dot is 1. Limit on the left-hand side function is approaching, that's, oh, let's use it. Left-hand side at 4, the limit is 2. The right-hand side, function is going down, down. Function is approaching big negative numbers. The same. Yeah. And this one, we may also say the limit does not exist on the right-hand side, but we know that it's negative infinity because we're using these details. Different limits, different behavior, limit on both sides, limit does not exist. Okay, 5, no problem at all. Continuity, function is continuous. Limit is the same like the value 1. Yeah, I think it is 1. Okay. Now let's look at a couple of limits laws, but we remember all of them because we will try to compute and analyze more limits. When we have a limit as x approaches a of the function f of x and g of x, and in order to use this property, these limits, they have to exist. Yes? We're assuming that they exist, meaning that even if the limit is infinity, yes, then the limit does not exist. I mean, infinity is not really an existence number. That means they have to exist as a one finite number. Then we may apply these rules. Limit of the sum and difference is the sum and difference of two limits. Limit of the constant is constant, constant multiple. Then we will focus only on the limit of the function, the variables, and constant will stay outside. Limit of the product is product of two limits. Limit of the quotient is the quotient of two limits if limit from the denominator is not 0. And assuming that both of them exist, because this is, yes, sometimes the number 4, number 5 are a little bit confusing. I mean, all of them, even addition, subtraction. Yeah? Just we have to know that we may apply this if the limits exist. And then limit of the power function is the power of the limit of the nth root is the nth root of that limit. Yeah? Thinking about existence and continuity of this. And the most popular property, direct substitution, if function is continuous, because I did type that function has to be polynomial or rational function, and A is in the domain because polynomials are continuous functions everywhere. Rational functions are continuous on the domain. But in general, if the function is continuous at A, then A, of course, is in the domain, then the limit is always the same like the value. We just have this example on the graph. Okay, let's see. We may try to figure out all of these limits. Assume that the limit as x approaches 6 of the function f of x is 4, exists. For each part below, calculate the limit or determine that does not exist. If the limit is infinity or negative infinity, please say so. Okay, limit as x approaches 6, f of x squared. Function f of x, the limit is 4, limit of the power is the power of the function. I mean power of the limit, that's we can just say 16. We don't have to rewrite this. Okay, this one, limit of as x approaches 6, 1 over f of x. I can use this property because we don't have to rewrite. Limit of the constant is constant. Limit of f of x at 6 is 4. The final answer is 1, 4. Okay. This one is a product. That means we will find the limit of x times limit of f of x as x approaches 6. X is just 6, direct substitution, continuity, and this limit is 4, 24. Okay, now if I compute that limit and this one, we can see what's happened. This limit as x approaches 6 of f of x, it is 4, but when I do the direct substitution, we will have 0 squared. That's a little bit weird. That's we cannot really use the property of the quotient because denominator is 0. And we remember from the previous slide, you may come back and look at the slide, the laws. We may apply this if the limit of the denominator is not 0. Okay, but we also know, because we went through all of the concept, we know what to do. Let me write again. This limit is 4. This will be 6 minus 6 squared will be 0, but will be positive 0. We know I'm writing 0, but it's almost 0. It's just a small number. Yeah, we can see, I can indicate this. It's just a small number because even if we're using direct substitution and I'm grabbing 6 and replacing x with 6, we know that it's not exactly 6. Yeah, it's like 6.0001 or 5.99999. Yeah, extremely close, sufficiently close, arbitrary close to 6. Then that is almost 0. And since we're squaring, this difference will be, squared will be always positive. And now we know constant number over small number is a big number. And positive 4, positive 0, it's positive infinity. So we remember this. 1 over small is big. Small is 0, big is infinity. It's extremely informal, but it's helpful. And always add the arithmetic. Plus and minus, we have to always adjust this. Okay, now what's going on here? When I compute the limit on the numerator, we will have 1 minus 4 because limit of f of x is 4. This one is again 0, positive. That means now we have negative 3 over small number, almost 0. A number over constant over small number is a big number, but now we have negative over positive, negative infinity. That's what I was referring to respecting arithmetic, the numbers, okay? But please remember, 1 over small is big, 1 over 0 is infinity, plus or minus. Okay, and this one, we have limit of the numerator of f of x as x approaches 6 is 4, and then we have 6 minus 6, 0. But we don't know because if x is if x is approaching 6 from the right hand side, let's say right hand side, then this will be 6.0001 minus 6. It will be positive number. That means we will have positive infinity. Yes, a constant over small number is a big number. Or we can have a situation and when x is approaching 6 from the left-hand side. And that means this is still 4. This is still 4 because on both sides the limit exists. That means from both sides is the same. 5.999 minus 6, it's 0, but it's small, it's negative. Constant over small number, 4 over small number is a big number, but it's negative. So we can see positive, negative. Then what I supposed to say that limit does not exist. Yes, we do not have, I can maybe say this limit as x approaches 6, f of x, x minus 6, does not exist. This one also not existence. Yeah, but does not exist because we do have this and we do, I just wanted to make the notes clear for my students. Okay, beautiful. Okay, that's the thing. D and E was okay, but F we don't know. From the right and from the left-hand side, different behavior. Okay, perfect. And we can apply, I just type this, if both of them exist. I didn't apply the laws because we had 0 in the denominators. Okay, let's keep moving. Exercise number 3. Suppose that the limit as x approaches 0, g of x is 0. Calculate the limit g of x over x squared. Okay, that means this is 0. Right, g of x, the limit of g of x is 0, 0 squared is 0, 0 over 0. We know that is indeterminate form. Now, yes, we don't know exactly, because the problem is with g of x, we don't know like what kind of zero it is. Function g of x, let's say this, function g of x could be x squared. And that's what I can do. Let's pretend that function g of x is x squared. The limit is 0. Yeah, that's mean I'm trying to show that we can satisfy this limit with different formulas. Now, let's actually say that function g of x is just x. And limit at 0 is also 0. Yeah, we're still good. And maybe one more. Let's pretend, yes, that function g of x is x cubed. Okay, we definitely satisfying all of this condition. Now, what about this limit? Limit of g of x over x squared. Yes, limit, and g of x, we decided in our 1, 2, 3. The first is x squared. And x squared over x squared, we will simplify as 1. Limit of the constant is a constant. As we can see, we have 1. We have this answer, yes. Let's check this. Limit as x goes to 0, g of x over x squared. What happened if actually g of x is x? If this is x, oh, too far, then what's happened? 1 over x. Yes, and 1 over x, 1 over small number is a big number, but we have to specify it if it's right on the left-hand side. If it's right, will be positive. If it's left-hand side, will be negative. That means I can actually say that both one-sided limits are different, because I will not change. We do not have specified left or the right-hand side. We can just see this limit does not exist, but it's positive, negative, infinity from the right, left-hand side, respectively. Okay, and then the last quotient, limit as x approaches 0, and g of x could be x cubed. Then this is just x after simplifying, and continuity 0. I mean, direct substitution, because we still have no value for the original quotient. Okay, that's we can see 1. This could be positive, negative, infinity. If we specify the side, the limit does not exist actually at 0 and 0. So that means we have 0, we have non-existence value, and we have finite number. Yeah? It could be anything. We don't know. That means we may see the final answer is this one. We have not enough information. I did pretend the formulas. Yeah, that's the formulas of g of x, but we don't know. Could be anything. That's the reason that we have to be really careful when we do direct substitution and we getting 0 over 0. It could be anything. We have to really investigate the formulas. Okay, answer E. Okay, similar. Suppose that the limit at 0 of f of x over x is 10. Calculate the limit of f of x at 0. But now we can see what's happened. We have a finite number. X is approaching 0. That's when we think about, oh, I just wanted direct substitution. This is 0. And we know the final answer. The final answer. This is actually, let me write. Then we will have the answer. Of course, we cannot really use, because this is 0. We cannot really use that property, but okay, x is 0, I can put 0, but we know that the final answer is a finite number. Yes, it's 10. Having 0 in the denominator. If this will be a finite number, like let's say 1 or 10, 1 over 0 is a big number. 10 over 0 is a big number. That means we will not have 10. Since we have a finite number and 0 in the denominator, we know that we definitely dealing with indeterminate form. That means this limit must be also 0. And I think we have enough information in this case. And we can come, let's come back for a second. We can see finite number. Yes, it is 0 over 0. This goes to 0, this goes to 0. I can even write this. This is 0 over 0. Actually, all of them, when we do the substitution, yes, when we will do the substitution in that row. But only the indeterminate form with 0 in the denominator, and of course, the 0 can give us a finite number. That means this limit must be 0, just because the final answer is a finite number. If this will be infinity, then we will have not enough information, but it will be 1 or 10. But if to figure out what is this limit, then we don't know. Yeah, if this will be the other way, I mean, if we will not know that value 10. But since 0 over 0 is an indeterminate form and we know the final answer, I mean, having 0 in the denominator, because this is our answer, then we will assume that this is 0, because 0 over 0 could give us a finite number. That's the only case. Okay, this has to be 0. Okay, now we have some fancy function and the limit. As x approaches -4, x squared plus 4x over square root x squared minus 7 minus 3. When we substitute, direct substitution, let's see what's happened. 16 minus 16, 0. 16 minus 7, 9, square root of 9, 3, 3 minus 3, 0. Okay, so indefinitely denominator 0 and numerator 0. We still don't know, because even if we have 0 over 0, could be anything, could be 0, could be a finite number, could be like finite number, or could be infinity. So we have to be careful. What we can do for this, I can possibly factor out this, but for the root expression, we remember that one of the good way to rewrite this, we will multiply by the conjugate, square root plus 3, and the same radicand. Yeah, that's when you can see I copy this expression, but I create the conjugate. Okay, let's see what we have. -4. I mean, I will not distribute this x squared minus 7 plus 3, but I will distribute this square root minus 3, square root plus 3. It's like a minus b, a plus b. In order to FOIL really quickly, we will square the first quantity, square the second, and minus, but you can also FOIL. Okay, squaring the square root, only the quantity inside will stay, minus squaring 3 will be 9. Okay, and let's see what we have, because we're looking for some common factor to be cancelled out. Oh, -7. Okay, x squared minus 7 minus 9, it's actually x squared minus 16, and I can factor out x minus 4, x plus 4, and we nicely see the common factor, and that's actually the 0. Yeah, because -4 plus 4 is 0. That's we did cancel out that 0. Function is still not defined at -4, but I hope the limit will exist. Let's substitute -4, it will be 16 minus 7, 9. Okay, and negative 4 minus 4. Okay, what we have, I can erase this. We should not put two equal signs in one line. Negative 4 times 6 and negative 8. The final answer is, I'm just trying to simplify, negative over negative. It will be 3. Let me double check. This is 1/2, 6, 1/2 of 6 is 3, okay? But this is limit, yes? We have to be careful. At negative 4, the limit is 3. We don't know how function looks like, and we have no value, yes? Function doesn't have a value at negative 4. Value does not exist. Just the limit is 3. And what I erase? Conjugate, a minus b, a plus b, but we know this from algebra. Everybody knows this, okay? Perfect. Exercise number 6. Limit as h goes to 0, 1 over 3 minus h minus 1/3 over h. When we do the direct substitution, h, 1/3 minus 1/3, it is 0, h is 0, 0 over 0. And we can definitely rearrange probably the common denominator on the top and simplifying to one fraction, hopefully will give us common factor, and that factor will be cancelled out, and that's the 0. But we may also notice, I know that we're reviewing limits, but you may notice that this limit represents the derivative of a function at a certain point. Yes, the point is 3, and function is, where can I write? Function is just 1 over x. Yes, that means you may, if we know a little bit more, if we know the next chapter, the derivatives, you may even get the answer this way, because derivative of 1 over x is negative 1 over x squared. I know that is because this is x to the negative 1. And then when we substitute 3, negative 1, 9. And that means this is derivative at 3. The final answer is negative 1, 9. Nice. Okay, that means I hope you can use the power formula and get it. Let's actually check. We can still do without applying the calculus concept. I will multiply, because the common denominator is 3 minus h times 3. Let me write this way. 3 minus h times 3. I will multiply each term. I will distribute this, and I will just rewrite as a product. Limit as h goes to 0. The first fraction, 1 over 3 minus h, multiplying by this, we can cancel out this, only 3 will stay. Minus, multiplying 1/3 times this, we can cancel out 3, and 3 minus h will stay. I hope, let me just keep this. And in the denominator, I will just keep the product, because I need that h. I need that h to be cancelled out eventually. Okay, 3 minus 3 and negative will give us positive h. Something is that I think, oh, 1 second, I'm just looking because, one thing, we have to have plus h. Okay, let's do it. Of course, we have a plus h. I just realized that we will have, because I need negative. Negative 3 minus 3, and that negative will affect h will be negative h. That means this is just a typo, because, okay, I can write a definition in a minute of the derivative. It's supposed to be plus h. I think I saw it plus h. Then this is derivative of the function 1 over x at 3. Okay, but let's distribute 3 minus 3 is 0, negative h, and then we have h, 3 plus h. And then we can cancel out, but we need that negative. Let me write here, limit -1, 3 plus h. And then h is 0. I can do the direct substitution. H is 0, and the final answer will be 3 times 3, 9, -1. Okay, it is the same answer. Okay, one more time. I can write, or maybe I can write here, limit as h goes to 0, f of a plus h, of course, f of a over h. Yeah? This is derivative at a. I know this is the next chapter, yes, chapter 3, that's h, but it's plus h, okay? Just didn't even, okay. But anyway, even if it's even because we're not even talking about the derivatives, even if this is minus, like I did, the final answer will be 1/9. That means it's not exactly the derivative. Okay? It's not exactly a definition of the derivative. This is a definition. That means if the function, you can even think this way, if the function is 1 over x, to evaluate 1 over x at 3, plus h, we will put 1 over 3 plus h, minus f of 3, 1 over 3. Okay, just to know this. But of course, this was a typo because my intention was to actually have to see the derivative of the function 1 over x. But we can see the upper part of the solution. Yeah? Even computing the limit with minus, then it's not then we will skip that part. We will just do the algebra. Yeah, that's me. Please definitely know how to simplify algebraically this type of indeterminate form 0 over 0. Yeah, that means that just the final answer will be positive 1. But my intention was -1/9. Okay, exercise, the next one, number 7. Okay, evaluate the limit at 0, sine of x plus tangent of 3x over x. We can see it's 0 over 0 because sine at 0 is 0, tangent at 0 is 0. Let's actually do this, sine of x over x and tan of 3x over x. And as x goes to 0, sine of x over x is 1, and also tan of x over x, but we have that 3. That's we definitely need the same quantity, the same as this. That means I can multiply by 3 and divide, multiply and divide. And this expression, it is 1 as x goes to 0, and this will stay 3. Okay, 1 plus 3, 4. The final answer is 4. But what I was using, I was definitely using the property sine of x over identical x at 0. It's 1. And also we may directly apply tan of x over x. It is 1, but just because tangent is sine over cosine. Cosine at 0 is 1, but sine of x over x, that means this is the same, yeah, almost the same. Okay, done. Now, exercise number 8. For what values of the constant c will the function f have a limit as x approaches 2? So we definitely see on the left-hand side at 2, that formula, on the right-hand side at 2, this formula. Function is not defined at 2. We have no value. But even if we have no value, the open dot, we may have a limit. What we have to check? We have to check if the limit as x approaches 2 from the left-hand side, sine of cx minus 2 over x minus 2 must be the same. I'm checking, yes, we can figure out Let me actually write this on the right-hand side. And okay, that's me. No, because we have this coefficient. We will figure out, yes, what is the value of C, hopefully, if the function will satisfy the equation that I just said. The left-hand side must be the same like the right-hand side limit. Okay? Then if the both one-sided limits are the same, limit exists, and f has a limit as x approaches 2. Yeah? Then this limit at 2 of the function f of x, we don't know what is the limit. We can compute, but we're not looking, but the limit will exist. Okay, that's what we can do. Since it's indeterminate forms, 0 over 0, 0 over 0. Let's figure out. Let's look at the left-hand side. We have sine of 0 over 0, but we can see we do not have identical 0 because we have that c. I can multiply by c, but since I am multiplying the denominator, I have to multiply the numerator. And now when you look at this, as x approaches 2, because 2 minus 2 is 0. It is sine of 0, that's 0, and over identical 0. That means this limit is 1. However, outside the coefficient c stays. That means it's just c times 1. Okay, on this, that's the limit. Now, this one is 0 over 0. First of all, let's maybe rewrite one more time. X minus 2. We have to, if we have absolute value, we have to rewrite without the absolute value. If the quantity inside absolute value is positive, for instance, like absolute value of 5 is 5, absolute value of 100 is 100. We may ignore absolute value, no problem. If the quantity is positive, we have to check. But if the quantity is negative, absolute value of -5 is not -5. I have to take this quantity and put extra negative to make the quantity positive. That's, let's do it. Let's check if quantity 2 minus x is positive or negative. 2 from the right-hand side. That means this is like 2.01. When we subtract 2 minus 2.01 or 2.0001, we will always get negative quantity because 2 is from the right-hand side. It's greater than, yes, a little bit greater. That means this quantity inside is always negative. 2 minus x, it's always negative. I will make it positive. Okay, now we can simplify, and because we have 2 minus x, when I distribute, we will have -2, negative and negative x, positive x. Actually, it is 1. Limit of the constant is 1. That means the constant c is 1. Okay, the constant c is 1. Then the limit exists. I don't know what is the limit. We can compute. If the constant c is 1, actually the limit on the left and the right-hand side is 1. That means this is also 1. Not always, yeah, not always will be the same thing, like the coefficient and the limit. In this case it is, but the constant c is 1. That's what we were looking for. If the constant c is 1, you may compute the limits on both sides again, and you will get the same answer. Okay, excellent, good limits, yeah, on the left and the right-hand side. Make sure that you understand them. Okay, continuity, I think I mentioned this a couple of times. Function f is continuous at the number a if a is in the domain and the value is defined, and then the limit exists, and actually then limit is the same like the value. Yeah. Also, for the limit to exist, sometimes we have to check the left-hand side must be the same like the limit of the function on the right-hand side. Yes, if the limits are the same, then the limit exists. The limit exists. And then if the value is the same, function is continuous. Okay, let's look at this exercise. For what values of b, for this function, for this piecewise defined function, function is actually continuous. Okay, everywhere. That's what we can see. Quadratic function, continuous. Constant, continuous. Third degree polynomial, continuous. Function is continuous everywhere, but we have to investigate that turning point, 1. Because at 1, from the left-hand side, we can see as x is approaching 1 from the left-hand side, this is the formula. And this is the formula. Exactly the value of the function is b. And the right-hand side, for x is greater than 1, it's the right-hand side, we do have this function. I mean, first of all, and we also have to say this has to be the same like the value. That's mean limit on the left, limit on the right, and the value, they have to be the same. And actually value is value is b. And we're looking for b. Let me squeeze this. I mean, it has to be the same like the value, and this is b. That means let's actually figure out if we can find out what it is. Okay, limit on the left. Limit on the left will be 1 plus a times 1. 1 plus a. Limit on the right will be 2 times 1 minus 2a plus 5. From this two one-sided limits, we can compute a. 3a, 7, 6, a is 2. But this is a. But if a is 2, we can find out what is the limit on the left-hand side. Yeah, the left-hand side limit will be 1 plus a times 1. This means it will be 1 plus a times 1. The limit is 3. Now, on the right-hand side, it has to be the same. I can say right away it is 3, but let's check. 2 times 1 minus 2 times a is 2, plus 5. It is 3, 7 minus 4, yeah, because it's 7 minus 4, it is 3. That means if this limit is 3, then value must be the same like the limit, because it happens that it's the same. B is, and value is b, b is 3. Okay, that's a nice question. But definitely the limits, yeah, on the left and on the right-hand side. Okay, they have to be the same for the continuity. And the value, we cannot afford removable discontinuity. Okay, now couple of true and false statement. Let's see. If the limit as x approaches 1, f of x over x minus 1 is equal to 10, then limit of f of x is 0 at 1. Yes, because then we have a finite number, 0 in the denominator, then we need 0, we need indeterminate form, 0 over 0. Yes, this is true. If limit at 1 from the left-hand side is positive infinity, 1, this is 1. From the left-hand side is positive infinity. Then function is discontinuous at 1. Of course it is. And that means this is true, because we have discontinuity. Even if I will have some, whatever will happen on, and that means definitely it is discontinuous at 1, but we may, I'm just thinking, we may also say it's continuous on the left-hand side. Because we remember we have one-sided continuity. You can even see I draw, if function goes up, looks like a nice continuous, but it says discontinuous at 1. That means yes, because we don't know the situation on the right-hand side. If this will be discontinuous at 1 from the left-hand side, that's actually false, because it is continuous on the left-hand side. But no, at 1, we have to know both sides. That means this is true. We do have discontinuity. Okay, and the third statement, if f is continuous at 1, then the limit is the same like the value. Of course, that's the continuity means that the limit is the same like the value. True, true, true. Exercise number 11. If limit as x approaches 1 of f of x is 5 and the value is 3, then function has a removable discontinuity at 1. Of course. At 1, value is 3 and limit is 5. Limit is 5, value is 3. Yes, it is removable discontinuity. If limit on the left and the right-hand side is the same, then function is continuous at 1. No, that's false. That's false because limit at 1 could be, let's say, 5. Yeah, it's the same. It's the same limit. But value at 1 could be somewhere else. Let's say it's 6. That means this is actually false. That's false statement. Function is not continuous. Okay, and now just the properties. Limit at 5 is 2, limit at 5 is 3 for f and g respectively. And now just the property, they are defined, they exist actually. 3 times 2, because this limit is 2, 2 times 3, 6 plus 6, yes, this is true. True statement. Okay, nice. Exercise number 12. Limits at infinity. Let's determine. Limits at infinity, we definitely know that we have to look at the leading terms only, leading terms. Okay? That means this is the leading term and this is the leading term. Okay, square root of 16 is 4 and a square root of x squared. This is the question. Yeah, let's see, because this one is at negative infinity. If x is positive, I can simply say this is x. Yeah, because x squared, to simplify, we know that we have to put absolute value. But if x is positive, like when x goes to positive infinity, absolute value of positive number is just a positive number. Okay, that's me. Let's put this down. Okay, that's me. Now we will have actually 4x over 4x. I mean the limit. I can maybe write this. Square root is, yeah, the limit is 1. Now, the same thing, limit at negative infinity. As x goes to negative infinity, square root of 16, 4, square root of x squared, and this is 4x, nothing changed. And now, square root of x squared is still absolute value. But if x is negative or going to the negative infinity, then this quantity is negative. I have to make it positive. Okay, that means we will have negative x. And when we simplify, it will be negative 1. So please be extremely careful. Okay? Please be extremely careful with this. Also, what we can say, let's look at like just in general, square root is always positive. 4x plus 3, when x is positive number, it will be positive. That means only positive answers are our options. Or maybe infinity, I don't know. We have to always check the degree and the leading terms. But this is definitely positive. This function definitely is positive. Now, looking at this, x is going to the negative infinity. Square root is always positive, and we will even square it. We can see positive, right? But 4x plus 3 will be negative at negative infinity. That means positive over negative. The answer must be negative. And this will be the option, and then we have to do our arithmetic. And that's also a good way of thinking about the sign of this type of limits. Okay, let's look at the next limit at Okay, this limit is at negative infinity, but we do not have even root, we have cube root. But also, we will limits at infinity, we have to focus on the leading terms. But in general, before we start, simplifying, let's look at the sign. We will take to the power of 6 negative number. That means this will be positive, cube root of the positive. The sign of the numerator will be positive, denominator will be positive. That means now the negative answer is not an option. We have to figure out maybe negative infinity, but no function will be positive. Okay, I mean, that's how we can investigate, and not even mentioning cube root at I mean, we will take to the power of 6. This will be positive infinity, and this will be positive infinity. We actually have in another indeterminate form. And the same was, but what we will do, let's focus on the leading terms. That's mean cube root of x to the power of 6, because we remember rest of the terms will disappear. And yeah, this is just, it is x squared, because we will divide 6 by 3. This is x squared, and actually it is 1. Limit of the constant is constant. So the limit is 1. But we knew it, that function actually attains positive values at negative infinity, because positive and positive, everything is actually even powers. And that's also a good point to check. Okay, exercise number 14. How arctangent behaves at positive infinity. We know the graph of arctangent, extremely helpful. Arctangent looks like this, and we do have, because we just flipped negative pi over 2 and positive pi over 2. That means at positive infinity, arctangent goes to pi over 2. At negative infinity, negative. That means it's so helpful. This is arctangent of x. Also, I didn't have this, I'm just thinking now, we also use quite a lot this behavior, natural log of x at 0 from the right hand side. How function ln of x looks like this. This is 1, we know the domain, and this is 0 from the right hand side. Function goes down, negative infinity. Please also keep this in mind, negative infinity. Arctangent log, natural log, it's quite helpful function. Okay, and then I have the last exercise, kind of like summary of limits. Okay, find the asymptotes of the function, rational function, x squared minus 1 over x minus 1, x plus 2. And based on the options A, B, C, D, and E, we see x and y equations. X is the vertical, y is the horizontal line. Okay, that means first of all, let's actually start from horizontal. Horizontal asymptotes, we just have to compute limits at positive infinity and negative infinity. It's been horizontal asymptote. When I distribute this, we will have x squared. It will be plus x minus 2. And actually the same thing, sometimes the limits we know could be different. Okay, it's x squared, the leading term, and x squared is identical. The limit is 1, and the same for this one. I mean, the limit is 1, then we can say y equals to 1 is a horizontal asymptote. And one more time, in order to find the horizontal asymptote, you will compute limits of infinity. We may have different at positive and negative. In this case, it's the same, 1. Okay, now for the vertical asymptote. asymptotes. Yeah, we can also have 2. We can have infinitely many for the vertical asymptotes. Okay, that's mean the good candidates are always the numbers that are not in the domain. Because we can see x cannot be 1, x cannot be -2. Yeah? But please do not -2. We can nicely see the option with -2 and 1 and y equals to 1 as a horizontal asymptote. I will be extremely careful, because theoretically, by definition, vertical asymptotes, in order for the vertical line to be the vertical asymptotes, one-sided limit or both sides, the limit must be positive or negative infinity. Yeah, that means this is the thing. We have to compute a limit as x goes to 1 of this function. I can maybe distribute, not distribute, actually, the opposite factor form. And now we can see that because 1 is giving me 0 in the denominator, but I think I can remove that 0. If I remove that 0, 1 over 0, 1 over small number is a big number. I remove that option. 1 plus 1, 2, 1 plus 2, 3. It's a finite number. That means this is no vertical asymptotes, because it will be actually removable, correct? 1 and 2/3. It will be no value, of course, no value, but the limit exists as a finite number. That means it's no value, but it's not a vertical asymptote. Okay, that means it's not a vertical asymptote. Okay, of course, this is not an option because we have to have this. Okay, that means let's see, probably this one, right? But I don't know, because that's the only option that we have. 0, no, 0 is not the, okay, but let's check. Yeah, if I will compute limit at -2, x minus 1, x plus 1, x minus 1, x plus 2. We eliminate 0, but not this one. Yeah, x plus 1, x plus 2. And x is approaching -2. -2 plus 1 is -1. -2 plus 2, it is 0. That means -1 over 0 over small number. It will be big number. However, we have to know if, the side. That means we will say, oh no, this is correct. I didn't want. Let's say from the right-hand side. Yeah, just one side that is okay. We can investigate the other side too. -2 from the right-hand side is -1, -1.9. -1.9 plus 2 will give us positive. Negative over positive is negative, but it's definitely infinity, because that x plus 2 will be never eliminated. Yeah, that means I don't like saying these shortcuts, but if you can simplify a factor, then this is not an vertical asymptote, because it's no more 0 in the denominator. We need that factor, we need that 0 in the denominator. Yes, -2 is giving us 0, and this cannot be cancelled out. Constant over 0, constant over small number, actually, it's a big number, infinity, and this indicates, that means this is a vertical asymptote. Okay, this actually, it's related to both. Okay, that means this is the final answer. -2, x equals to -2 will be an asymptote, because I can maybe use that graph. It's a little bit small, but this will be asymptote. On the right-hand side, function goes down and probably goes up. Oh, we do have a horizontal asymptote. Actually, let's just, as a final, I can quickly add a slide because I don't feel like squeezing. Let's just see. You can try to draw the scenario just in case, but let's nicely put this. Yeah, we did have the situation 1. Okay, limit at 1 is 2/3. limit at -2 is actually, and we also have 1, the horizontal asymptote. That's x, that's y, and this is y. So and what is the y-intercept? When x is 0, we will have -1, -2, 1/2, 1/2. Oh, where is 1/2? 1/2 is lower than 2/3, correct? I mean, this is 2/3, this is 1/2. Okay, that means looks like, I don't know exactly, but okay. Oh, okay, I didn't compute the x-intercept. X-intercept will be on the 1 and -1. But 1, we do not have the value -1. Okay, I'm almost right. And I'm assuming it will be like this because on the other side will be positive infinity. We've got negative infinity on the right-hand side, and it will be positive. And we have to respect the horizontal asymptote. It means horizontal asymptote y equals to 1, vertical asymptote x equals to -2. No asymptote at 1. That means please be extremely careful. It's a nice question, but I know that you probably know the shortcut. As soon as we cancel out, it's not an asymptote, but just knowing the nice theoretical part hidden behind. Okay, please rewatch this session, redo all of these problems, and you will be a master with the limits. Yes, enjoy the limits review. Thank you.